Today we're working with Unit 1, Lesson 5, talking about coordinate moves. Our goal today is to be able to transform figures and see what happens to the coordinates of the points. We're going to start by talking directly about translating coordinates. The first thing that we're going to do is we're going to select all the translations that take triangle T to triangle U. There may be more than one correct answer. As we look at this ordered or this coordinate plane with these graphed triangles on it, our goal is to be able to take or to figure out which of these four options take triangle T to triangle U. What that means is that I'm going to, every move that is true that follows that order from, or that takes triangle T to triangle U has to be in that order. It has to be able to take this triangle T to triangle U. As we look at this, I'm going to draw the vectors from one point to another to see if that really happens. This one, first one, translate point -3, 0 to 1, 2. I already saw here that triangle T is congruent with triangle U, so I know that all translations will be absolutely true as long as they follow the correct vector. So I see that for this one, I need to look and see, are these 2 points corresponding? First off, top of this triangle is -3, 0. Top of this one's -1, 2, or excuse me, +1, 2. And I see that if I take my vector from -3, 0 to 1, 2, this is true as far as the translation goes, because I go from corresponding point on T to the corresponding point on U. Number one is one of the correct answers. Number two says translate from point 2, 1 to -2, -1. Well, these are corresponding locations and corresponding points. However, since the directions say from this point to this point, that will not carry triangle T to triangle U. That would just carry triangle T using that vector. It would actually carry it back off of the page further this way because of the location of the figure. It could also be thought of as taking from this point to this point. What it looks like is that we actually have a translation along a vector that moves from here to here, not the correct way of triangle T to triangle U. So number two does not work. Number three, talking about from the point -4, -3 to the ordered pair, or the point 0, -1, we see that those are corresponding locations on the triangle. We also see that we are moving from T to U. This would be also another true translation. The final one will be taking a translation that moves from 1, 2 to 2, 1. In other words, what that would do is that would actually take our images, or our image, and translate that image one unit down and to the right. So what that would do, even though the vector is way over here, it would take our triangle right here and it would translate it right there. This does not take triangle T to triangle U. Instead, it just simply translates it down and to the right just a little bit. Option 4 does not work for translation that takes triangle T to triangle U. On the next page, we're reflecting points on a coordinate plane. So when we reflect the points, that's all we're going to reflect. Take a look at our directions. Here's a list of points, A, B, C, D, and E. On the coordinate plane, plot each point and label each with its coordinates. Okay, so we're going to start here, plot each point. So point A is going to be starting at the origin. Just a quick review of how to graph an ordered pair. We want to start right here, and we want to work off of the axes, or off of the coordinate pairs. So we have X and Y. Any point is always going to be labeled, or is always going to be listed as an X coordinate followed by a Y coordinate. This is what we mean by ordered pairs. X first, followed by Y. We use that same order when we plot our points by plotting the X coordinate first using the X axis, so left or right. And then we follow that with the Y coordinate up and down on the vertical axes. Our first point being 5/10 and 4, starting at the origin, I see a positive value, so I know I'm going to the right. And then I see another positive value for y, which indicates up. So I'm going to go half of a unit to the right and 4 units up. Remember that the directions say to label each with its coordinates. So each point, plot each point. This is point A, and its coordinates are 5/10 and 4. Point B, we go back to the origin. I see that the x coordinate is a negative coordinate indicating left, and then a y coordinate is positive. So we're going to go left 4 units and up 5 units to give us point B, which is there again at -4, +5. Whoops, I'm sorry. Let's look at those again just to make sure. Point A is at half of a unit to the right, 4 units up. Point B is 4 units left and 5 units up because I have a negative and a positive. Point C, we return back to the origin. The point C is at 7, 2. So we're going to go 7 units to the right, -2 units down for point C at 7, -2. D, we return back to the origin. D is at 6, 0. So we're going to go 6 units to the right and 0 units up or down, which remains on the line of reflection. Keep that in mind. We're going to come back to something interesting about that. The final point, point E, x coordinate is 0, so I don't go anywhere left and right. I simply follow the y coordinate of -3, down 3 units. This is point E, which is going to be, well, I know where this is going, so I'm going to put E up here. Sorry, that's kind of a bad spot. And this is 0, -3. The next directions here, once we have all those points, it does not say anything about connecting the points, so I'm just going to leave the points there. Point B says, using the x-axis as the line of reflection, plot the image of each point. Remember, when we plot the image, we're going to plot the reflected copy of each point. To help me to see this, I'm going to go ahead and set my pen, my blue pen. I'm going to plot my images with red, but I'm going to set my blue pen here to be able to see where the line of reflection is, to hopefully give a little bit more clarity to what we mean by reflect. I'll just work from left to right and start reflecting with B. A reflection across the x-axis means that I need to take point B an equal distance across the x-axis. So right now, the distance away from the x-axis for point B is 5 units. An equal distance on the opposite side would still be 5 units. So I'm going to be at my line, and then I'll be 1, 2, 3, 4, 5 units. Since we're reflecting directly across the x-axis, we need to remember that a reflection goes perpendicular to the line of reflection. Sometimes the line of reflection is called a perpendicular bisector. We want to plot the image of each point. There's that point there. You know, it seems kind of silly to leave that without anything. Letter C tells us to label the image of each point with its coordinates. So I know that when I label that, I need to include a label using a letter, right? This is called point B, but we need to be able to differentiate between B and its image. So we're going to go B prime, which is at -4, and now -5. Point E being at 0, -3, reflecting across the x-axis, 3 units away from it. So it will be 3 units on the opposite side of it, perpendicular, making this point at 0, 3, E prime at 0, 3. I go on to my next point of A, which is at half, 5/10 and 4. Again, reflecting perpendicular to the line of reflection, 4 units away. So I come down here 4 units away, and this point becomes A prime at 5/10 and -4. I come over here a little bit further. I see point C, which is at 7 and -2. So again, across the line, 2 units to put it right here. Now the question might be, what about D? Well, currently, D is not really represented. When I move my pen, I see that D is on the line of reflection. This is an exception when we're talking about our reflection piece. That point does not move because it's a part of the line of reflection. It's just the opposite side. So what we would do with that is still go ahead and label it as also D prime, which remains at 6, 0. Okay, I hope what you can see is the relationship between these two pieces. Again, using the right line of reflection, we want to recognize that there's an equal distance away from the line of reflection in a perpendicular or 90-degree direction. The line of reflection here is cuts in half the distance between these 2 points, as well as the distance between the E's and the A and A prime, as well as the C and C prime. D prime and D never moved because it was on the line of reflection. We can use this information to hopefully make a prediction for a rule that we can use when we're doing a reflection across x-axis. If I were given the point of 1310 and were to reflect that point using the x-axis as the line of reflection, what would be the coordinate of the image? Well, if I go back and look at this and I do a little bit of analysis, I see that the original point B was at -4, +5. B prime became -4, -5. E was at -0, -3 and changed to 0, +3 after the reflection across X. A from 5/10, +4 to 5/10, -4. C from 7/2 to 7, -2 to 7, oh my goodness, I've made a mistake, to 7, +2. And what I've noticed, or what I think I noticed, is a pattern here. I see that under a reflection across the x-axis, I see a vertical change. And under that vertical change, I only see the y coordinate changing. The x coordinate didn't ever change from its original. But the y coordinate always took on its opposite. What that tells me then is if the point 1310 were reflected across the x-axis as a line of reflection, then the new ordered pair for that would be 13, -10. Well, what if it's 13, -20? Well, under the same theory and the same rule that we talked about, where if I reflect across the x-axis, the x coordinate remains the same because it's on the same vertical line, but the y coordinate changes to its opposite because it's in its opposite location with regard to the y-axis. That would mean that 13, -20 becomes 13, +20. Now, the next one, 13 and 507. What? Hold on. That's really big. That's way off the coordinate plane. But can I still make that prediction? I should absolutely be able to make that prediction still, because that plane, we know that is going to continue to go on forever and ever. That's something that I need to be aware of, and something that I need to understand is that no matter how far in those numbers I go, the x and the y axes continue to move forever in both directions, up and down, left and right. So what I can do with this is make my prediction that 13, 570 will reflect to 13, -570. And my explanation that I'm going to say is I need to talk about how reflecting over the x, reflecting over or across, either one, x-axis is a vertical reflection. So only y coordinates change. And in this case, y coordinate becomes its opposite. For example, what we would look at is this. If we take a point that's at xy, we would see that that point prime across the x-axis would maintain its x-coordinate, but it would take on its opposite form of a y-coordinate. So if it was at -3 for the y, it would become +3, or +6, it would turn to -6 in this case. So then what happens if we think about it from the other or from another perspective, and we say point R has the coordinates 3, 2. Without graphing, predict the coordinates of the image of point R if point R reflected using the y-axis as the line of reflection. I'd like to take a minute to go ahead and pause the video and think about point R where it's at 3, 2, and how under a reflection across the y-axis, how that would change. Do it. Pause the video. Make a prediction. Okay, welcome back. R prime, we made our prediction. I'm not going to tell you what my prediction is. I'm actually going to go ahead and go to the graph and look at this, and it says check your answer by finding the image of R on the graph. Well, that image of R, if we're looking at the y-axis being our line of reflection, I see that I'm going to go across this line. So I have 3 units away from this line, so I need to be 3 more units on the opposite side to make point R prime. I labeled my image as R prime, and I look to see what are the coordinates of that image. R prime is at -3, +2. And now I need to look back, and I need to check on my prediction. How did you do? Was your prediction -3, 2? If it was not, please review what we've talked about with R. If that's the vertical line, we're coming across the vertical line. Remember, we have to have a perpendicular relationship that takes a segment between these 2 points, the original and its prime, and must be perpendicular to the line of reflection. So the line of reflection is the perpendicular bisector of that segment. So let's say this. Suppose you reflect a point using the y-axis as a line of reflection. How would you describe its image? Well, I think we could go back and we could look at our description here when we understood that reflecting over the x-axis is a vertical reflection, so only the y-coordinate changed. I think we could say pretty much the same thing. Reflecting over the y-axis is a horizontal reflection, or horizontal reflection. So only the x coordinate changes. The x coordinate becomes its opposite. Our example is going to be this. If we're looking at a point, in this case, we're talking about R being a point, and we'll say R is the point, and we start out in the location of X, Y, and we reflect across the y-axis, we will see R prime taking on its opposite location on the x-axis, but maintaining its same position on the y-axis. Hopefully this is making sense. Pause the video for a moment, review over the other stuff, see if you have any questions, and then send me some feedback if you do. Okay, now you've had some time to think, perhaps you've sent me some feedback. We're going to talk about transformations of a segment. Transforming a segment on a coordinate plane becomes, I feel, a lot easier than what we had seen in previous rotations, because we have some different lines to work off of. It doesn't necessarily make it easier or better, but it does give us a different opportunity. In this little segment, we are working on rotation of the segment AB. Now with the rotation of the segment AB, I'm going to go ahead and make this line a little bit darker so we can see it. I'm going to use my patty paper so we can follow along. But with that rotation here, we want to take this segment AB, and we're supposed to rotate 90 degrees. Well, that rotation of 90 degrees, in this case counterclockwise, I can make a good guess and I can make a good estimate using since I have a coordinate plane under this and I have the boxes, it does give me a little bit of help to kind of figure out where 90 degrees is. I think that it should end right about here. I mean, it's pretty likely that I'm going to end up, since it was on an intersection of 2 lines here, that A prime should end up being, or in this case C, the image of A, is going to end up on another spot. I should be pretty good at estimating 90 degrees by now, but I have a little strategy to help out with that. I think that A prime, or excuse me, in this case C, as the directions tell me right here, this would be point C. I think that it's going to be right here, and I really hope it is because I just wrote that in pen. Here's my strategy. I know that the corner of a piece of paper is 90 degrees. If I take that corner and I line it up with, this is actually a Post-it note. If I take that corner and I line it up right along this line, I can actually get a good visual picture of 90 degrees. And I see that, I got it right. This is 90 degrees right here. So point C being right there, that's definitely 90 degrees. I could be happy about that, but knowing that that's a little strategy, we don't always have a protractor to be able to tell us, well, where's 90 degrees? When I put that protractor out here as 90 degrees, I see that my point is definitely 90 degrees here, and I've got that there. But it's a little strategy. Generally, when we're doing math, we have paper, so using that piece of paper would be something that would be really helpful. We're going to label this not C prime, but as C. The ordered pair of C in this case is at 3, -2. Number 2 says rotate segment AB 90 degrees counterclockwise around center A. Well, if I'm going to do that, I'm going to go around center A now, counterclockwise. I'm going to do the same type of thing, counterclockwise, though. Uh-oh, did I do that? I did do it counterclockwise. Awesome. So around A counterclockwise. And my image here, I'm going to label the image of B as D. So again, I'm going to do the same thing. I'm going to take an estimate where it's at. So, but sometimes it's kind of hard. So we're going to put that one there. I'm just going to hover over where that should be, remove my paper. I believe it's going to be there. With the protractor, I can check it and see I did it right. Again, using our new strategy that you probably already knew, I can line this up, bottom edge along that line, 90 degrees, and I see that that's also a 90-degree angle. This point right here will be called D. We go ahead and sketch our line in here, our segment. Now it says rotate segment AB 90 degrees clockwise around 0, 0. Okay, well, if this is right here, here's some things I need to realize about when I'm rotating around 0, 0, around the origin. This segment AB is currently sitting here as a piece that's coming at 2 different locations, or a segment that's just on the coordinate plane. When I'm using 0, 0 as my center of rotation, it's going to be important that I recognize where those 90-degree angles are. Using the y-axis and the x-axis as a guide will definitely help us to do that. So when I see rotating the segment AB 90 degrees clockwise around center O, I'm going to put my pen right here and rotate clockwise from quadrant 1 down to quadrant 4, because that's a clockwise rotation. And I see that segment AB will be right here at 3, 0 and at 2, 4. So I'm going to go ahead. It says label the image of A as E. So we're going to take point A, and that one's going to be point E. And then it says label the image of B as F. Okay. What are the coordinates of E and F? Well, as we go down here, we see that coordinates of point E are at 3, 0. And we see that the coordinates of F are at 2, -4. I forgot to answer the other parts. It says, what are the coordinates of C? Up above, we saw that. I put that right here. C is at 3, -2, and D was at 1, 7. The last one, it says, compare the 2 90-degree counterclockwise rotations of segment AB. What is the same about the images in these rotations, and what is different? Well, when I go and compare these 2 segments, this one was a little bit different of EF. The 2 90-degree counterclockwise rotations that we worked off of. Well, here's what I see that's the same. Segment AD is parallel to segment BC. I also see that the length of the segment is still the same. And what else do you guys have? Make sure you tell me when you go ahead and put that into, or you pay attention to that when you get questions similar in homework. But I'm going to go and write that down. I see that segment DE, or excuse me, DA is parallel to segment BC. I see that DA is the same length as segment BC. As we get into slope, we'll find out that they have the same slope, which is what causes the lines to be parallel. What's different? Well, what is different is we use different centers of rotation, so they're in different locations. So different locations because of a different center of rotation. All right, let's go ahead and wrap it up. To summarize, today what we talked about is we can use coordinates to describe points and find patterns in the coordinates to do different transformations. We described that a translation is expressed by a sequence of horizontal and vertical translations. For example, segment AB is translated right, 3 and down. We've talked about that in past, but we're also talking about that we can translate along a vector from a single point to a single point. We can talk about point B is translated along vector B prime, or we can describe that as being translated down and 3 units to the right. The same type of translation that occurred over here. We also talked about reflecting a point across an axis changes the sign of one coordinate. When we talk about reflecting across the x-axis, we're talking about changing the y-coordinate to its opposite form. If it was at -3, it turns to +3. But when we go and we reflect across the y-axis, we see something different. We change the x-coordinate. For example, when we look at these pieces, keep that in mind that reflections across the x-axis, here we go from A to A prime. Reflecting these pieces, we notice that the x-coordinate remains the same, but again, reflecting across the x-axis, the y-coordinate changes. Likewise, when we reflect across the y-axis, we see that it's the x-coordinate that changes. We also talked a little bit about a rotation. We don't have all the tools that we need to be able to describe rotations in perfect order as far as on a coordinate plane, but we're going to be getting there. What we do know how to do still is we do know how to rotate 90 degrees around center 0, 0. Again, 90-degree rotations, we can use a compass or a protractor. We can use a little bit of help with our patty paper, or we can use the corner of a piece of paper as 90 degrees. The most important thing that we recognize is that when we name the rotation taking place, we name the figure that is being rotated, we name how many degrees, and we name a direction. This is kind of a long video. There's a lot packed into it. Feel free to rewatch it as many times as you want. Watch it the first time through. Hopefully you watched it at normal speed. If you want to watch it again, double the speed. You guys, find strategies that are going to work for watching these videos. Thanks for hanging in there. I'm going to make a separate video of your homework. Sorry, it glitched out a little bit. I'm going to make a separate video of your homework, and stay tuned. You guys are doing great.